Good afternoon, students. Welcome back to chemistry online class. See, in the yesterday's class, so we have completed nitric acid. Okay, manufacture of nitric acid by Wurtzbach process, the large scale, right? And also I told you regarding chemical properties, especially reactivity of concentrated nitric acid, especially with the metals and non-metals. Okay, and also oxo acids of the phosphorus, their structures and their characteristics we have completed yesterday. According to theory NCERT syllabus, now according to your deleted for annual examination, it is only 15 group, you have to study this much only. What I am going to today discuss is phosphorus. Phosphorus, allotropes of phosphorus, compounds of the phosphorus, okay, which is actually not in the syllabus, but you have to read it for need purpose. Don't read it for theory. This I am covering only exclusively for need purpose. Okay, right. Let us see now. Let us see now for that is phosphorus. Allotropes of phosphorus. Allotropes of phosphorus. See, many allotropes. Phosphorus exhibit allotropes. Three important allotropes: white phosphorus, red phosphorus, and black phosphorus. Actually, 5 varieties are there: white, red, black, violet, and scarlet. Okay, but for our syllabus, according to your NCERT textbook, we are supposed to study white phosphorus, red phosphorus, alpha black phosphorus, and beta black phosphorus. Okay, so let us study one by one. That means, what is this allotropy? This allotropy is nothing but it is a different form of a same substance. Different form of a same substance existing in equilibrium. Existing in equilibrium with each other at definite transition temperature. It is called allotropy, and compounds with the exhibit they are called allotropes. That means this phosphorus exhibit 3 allotropes. What are 3 allotropes? That is white phosphorus, okay, then red phosphorus, okay, and even third one is a black phosphorus. So here in this black phosphorus we have 2 varieties, alpha and beta. Black phosphorus and beta black phosphorus. Now let's give you structural features of white phosphorus, red phosphorus, and this alpha and beta black phosphorus one by one. Let us see. Okay. That means, the first I will compare white and red phosphorus. Right. White phosphorus, generally, when you discuss white phosphorus. Okay. Actually, you know that phosphorus exists in tetraatomic state, that is P4. P4 white, P4 red, we can write. Okay, red. Now, structurally, how we can differentiate white phosphorus and red phosphorus? Structurally, when you see, they are the crystalline forms. Remember, they are the crystalline forms of phosphorus. Crystalline solid state, not amorphous. They are crystalline forms. This white phosphorus is having a white translucent, okay, waxy solid. When we see it physically, it appears like a what? White translucent waxy solid. And this white phosphorus, right, it is having that is P4 tetrahedral structure. That means one phosphorus atom is surrounded by another, that is 4 phosphorus atom through 4 covalent bonds. Right? Right. Next, that means it will be having like this. Phosphorus 1, 2, and generally you can write over like this. Okay, phosphorus, phosphorus. This is the tetrahedral structure for white phosphorus, and it is having a bond angle 60 degree. Because of the 60 degree bond angle, it is having internal strain, angle strain of 24 degree 44 minutes. That's why, because of this angle strain, generally this white phosphorus is highly reactive. It is highly reactive. Due to what? Due to total internal, that is, strain of 24 degree 44 minutes. That means very important property to be remembered. It is highly reactive. Okay, it is highly reactive because of angle strain. Because of angle strain of 24 degree 44 minutes. That means generally normal tetrahedral angle is how much? There is a formula to calculate angle strain alpha 1 by 109 degree 28 minutes or 109 degree 5 minutes. Actually, according to our excited levels, minus normal bond angle. Okay, what it is? Normal bond angle. Normal bond angle is how much here? It is 60 or 60. 1 by 2. 109 degree 28 minutes minus 60. Okay, that means it will have 49 degree 28 minutes. When you convert this into the 1 degree 60 minutes, it will become 48 degree, okay, 88 minutes. Right? 48 degree 88 minutes. Therefore, if you cancel it, what will get? 24 degree 44 minutes. Like this. And generally, when you have this angle strain, they will have strain on the ring. Because of this, it is highly reactive. Highly reactive because of angle strain. And next one, it is insoluble. It is insoluble in water. Insoluble in water, but soluble in carbon disulfide. Yes, organic solvent carbon disulfide. And next, it glows in dark. Means when you heat it, it shows glows in dark. That is called chemilumini. Okay, sense. It shows chemiluminescence property. It means shines in the dark when it is heated. Why? Because it forms a respective oxide, phosphorus pentoxide, P2, P4O10, or you can also tell in the P2O5 whenever it reacts with the molecular oxygen. Right? See, it is having P4 tetrahedral structure, right? Highly reactive because of the angle strain of 24 degree 44 minutes. Insoluble in water, but readily soluble in carbon disulfide. It glows in the dark, and this is a highly reactive, most unstable and least dense, that is, and highly poisonous. It is highly poisonous. It is highly poisonous. That is allotrope in all these allotropes of the phosphorus. These are the structural features. Along with the diagram, they ask for 2 marks, you can write this. Even it includes theory as well as well. See, this point is important. Why it is reactive? Because of the angle strain. That's why white phosphorus is kept under, it is stored under, see, very interestingly, water, not kerosene. How sodium is kept under kerosene and paraffin oil? Because of this reactivity is kept under water. Right. So that's about structural feature of first allotrope of the phosphorus, that is called white phosphorus. Okay, I repeat, it is having tetrahedral, it is a white translucent waxy solid, crystalline form, having P4 tetrahedral structure, highly reactive because of angle strain, insoluble in water, soluble in carbon disulfide, glows in dark, that is the nuisance property, and highly poisonous allotrope of all these allotropes of the phosphorus. Okay, right. Now coming to next, this white phosphorus. Okay, next we compare with the red phosphorus. What is red phosphorus? And what is the transition of this white phosphorus? Now coming to the second one, that is red phosphorus. Red phosphorus. Okay, red phosphorus is actually another crystalline form of the phosphorus. Actually, it is obtained by first preparation. It is obtained by heating white phosphorus. Okay, white phosphorus to 573 Kelvin. This is the transition temperature for several days in the inert atmosphere. Remember, that means white phosphorus P4 white slowly transited to red phosphorus P4 red. That's what? Heating up to 573 Kelvin. That means you can write it as P4 white slowly get transited to P4, that is what? Red. Remember, P4 white to P4 red, and these are interconvertible. That's why they are for us. What? That means above 573 or up to 573 the heat will get P4 red. Below that 573 will get once again back P4 white. This is the transition temperature from phosphorus white to phosphorus red. Okay. Next, this structural features. The red phosphorus is having iron gray luster. Okay, and the white translucent solid, but this is having iron gray luster, means shining property. Okay, iron gray luster. Then this red phosphorus, it is insoluble. It is insoluble in both, that is water and carbon disulfide. Remember, very important. It is non-poisonous. Okay, it is reactive. And if non-poisonous, insoluble in both carbon, that is in reactivity, it is reactive, and it exists as polymeric tetrahedral units. Okay, very important. Polymeric tetrahedral units. Because of this, it will lose its angle strain and become okay, that is less reactive, not more reactive, it is less reactive. Why? Upon forming polymeric tetrahedral structure, they will lose their angle strain. That's why less reactive compared to white phosphorus, insoluble in both carbon disulfide and water, having iron gray luster, okay, which is crystalline state only, and it is in P4 tetrahedral structure, and it does not glow. Okay, it does not glow in dark. It does not show chemiluminescence property. Remember, this is the difference between white phosphorus and red phosphorus. Just observe, red phosphorus is obtained how? By heating same white phosphorus to 573 Kelvin for several days in the inert atmosphere. And it is having actually what? Polymeric tetrahedral units, tetrahedral structure. Because of this, we lose angle strain and become less reactive, non-poisonous, insoluble in both water and carbon dioxide. Okay, right. What is that, sir? Polymeric tetraeder structure. See, this is the actually like this lattice. These are the polymeric, that is units. That means, sir, it will lose its angle strain only on attachment. Okay, this is the polymeric actually. Polymeric P4 tetrahedral units. Okay, right. Like this, you will have these here. This angle strain gone. Like this, it will continue. Units, polymeric. So this is how we can differentiate white phosphorus and red phosphorus. Okay. But transition temperature is what? 573 Kelvin. If they ask you difference between white phosphorus and red phosphorus, easily. First, white phosphorus is the white translucent waxy solid, whereas this is a iron grey luster. Okay. White phosphorus is highly reactive because of angle strain. Red phosphorus is the less reactive because it will have loose angle strain. Why white phosphorus exists in P4 tetrahedral structure, whereas red phosphorus in a polymeric P4 tetrahedral structure. White phosphorus is insoluble in water but readily soluble in carbon disulfide, whereas red phosphorus insoluble both in water as well as carbon disulfide. Ne4. Okay, white phosphorus glows in dark but red phosphorus does not glow in dark. See, very simple. 4 to 5 differences you can easily make out in the form of points. Okay, right. After this, now this red phosphorus get slowly transited to alpha black phosphorus. Okay, and beta black phosphorus you can get it from white phosphorus itself. How? Let us see. Now this same red phosphorus, when it is, it means, mention what I told you, alpha black phosphorus. This alpha black phosphorus, right? It is obtained. When it is obtained, when red phosphorus is heated to 803 Kelvin. Remember, 803 Kelvin. So red phosphorus get transited to P4 red, get transited to what? Alpha black phosphorus. Okay, alpha black phosphorus. What is the transition temperature? 803 Kelvin. Remember. Up to 803, above 803 you will get, once again below you will get say red phosphorus. But this is having, okay, this is having monoclinic, these are grammatical sense, monoclinic and rhombohedral geometries are used. Structure effect, rhombohedral structure, and it sublimes in the air. It sublimes in the air, means directly convert from solid to gas in the air, not in the room temperature. This is alpha black phosphorus, remember. Okay, monoclinic and rhombohedral structures units, whereas beta black phosphorus is obtained when white phosphorus, okay, is heated to 473 Kelvin. Right? It having layered structure. Layered structure like that of graphite. Okay? So very simple. When you heat red phosphorus, first white phosphorus to 803 Kelvin, what you will get? 803 Kelvin. You will get. See, I am telling you, white phosphorus to 573 Kelvin, you will get red phosphorus, right? But the same red phosphorus, see, when it is heated further to 803 Kelvin, you will get alpha black phosphorus. But when white phosphorus is decreased to 100 Kelvin, you will get back beta black phosphorus. So don't get confused. White phosphorus get transited to red phosphorus at 573 Kelvin, whereas if you decrease below 100 Kelvin, you will get a beta black phosphorus. But red phosphorus, upon continue heating to 803 Kelvin, you will get a alpha black phosphorus. So like this, you have to remember this transition temperature, very important for CET purpose. That's why what I told you, what are allotropes? Allotropes are the different form of a same substance existing in equilibrium with each other at definite transition temperature. That's it. It's about the allotropes of the phosphorus. Okay, so don't read this for theory purpose, but you can read it for need purpose. That's why I am covering here in this class only, right? Okay. So not much wasting the time. This is the completion of allotropes of the phosphorus: white phosphorus, red phosphorus, and two types of varieties of black phosphorus: alpha and beta black phosphorus. Alpha I can get it by red phosphorus, beta I can get it by white phosphorus. Remember. Okay, right. So that's about allotropes of phosphorus. Now coming to compounds of the phosphorus. The first compound of the phosphorus is phosphine. Okay, phosphine, PH3. Name is phosphine. How phosphine is prepared? Method of preparation. It is having two important methods. One by using calcium phosphide by hydrolysis with the water and with the mineral acids, that is HCl. Okay, and laboratory method by using white phosphorus with a generally caustic soda. Also, you can prepare in the lab this phosphine gas. But this phosphine gas is highly poisonous gas. I will tell you later. First, general method. The general method, as far as this is concerned, is the highly poisonous gas. Method of preparation. Method of preparation. The first method of preparation, see, phosphine is prepared by just taking calcium phosphides. Calcium phosphide formula is Ca3P. Hydrolyzing with the water. Or calcium phosphide hydrolyzing with the mineral acid dilute HCl. Dilute mineral acid is HCl. Calcium phosphide. Please remember, student, try to remember like this. Calcium, you know, divalent cation, phosphide 3 minus. That is cross multiply, you get Ca3P. Okay. Right. Now see, this calcium phosphide on hydrolysis of the water will get target product phosphine P-3. Right. Along with the calcium hydroxide CaOH taken twice. First you have to write these products. Right. Now balance equation: 2 phosphorus multiplied by 2, 3 calcium multiplied by 3. Lastly go for hydrogen adsorption. 2 3s are 6 and 3 2s are 6. Total 12. Therefore 6 H2. See, oxygen also balanced, hydrogen is also balanced. Next you can prepare by hydrolysis of calcium phosphide with the water. Okay, we get phosphine and calcium hydroxide. Not only this, even by using dilute mineral acid, that is dilute HCl also can get it. See, same thing, that is phosphine PH3, we get it first, right? Plus this is CaCl2, this time calcium chloride. Same 2 PH3, 3 CaCl2, okay, 6 hydrogen atoms and 6 chlorine, therefore 6 HCl. Over and down. This is one important method of preparation of hydrolysis, especially as for Karnataka CET. Right? Okay. Now coming to next laboratory method of preparation, lab method, how it is prepared in the laboratory. In the laboratory, phosphine is prepared. This is important for 3 purposes. It asks you for 2 or 3 months. Okay, lab method, laboratory method, how it is prepared in the laboratory. Simple, by taking the white phosphorus, okay, P4 white phosphorus, that is heated with the caustic soda, sodium hydroxide, caustic soda, concentrated caustic soda in the presence of water. What you will get? A target product phosphine PS3, poisonous gas, plus sodium hypophosphate NaH2PO2. What you will get? Sodium hypophosphite. Remember, sodium hypophosphite. This is actually the expected product. That means in the laboratory, this poisonous gas phosphine is prepared by heating or by treating white phosphorus P4 white with caustic soda, highly concentrated caustic soda in the presence of water. What you will get? Phosphine, sodium hypophosphate. It's a disproportionation reaction. Here in phosphine it is -3, sodium hypophosphite generally it is +1. That means here 0 to -3. Here it is +1, +2, and it is -4, right? Therefore +1. That means it will undergo reduction as well as oxidation. This is the example of disproportionation reaction. Okay. When balancing the equation, in balancing the equation, just you can go through here. 3 hydrogen are here, therefore we multiply by 3, right? Then automatically 3Na or 3NaH2PO2 because 3 sodium atoms. Then you can go for lastly, what is this? Hydrogen as well as, that is oxygen. See, here 3 2 are 6, 6 plus 3, 9. Already 3 are here. So make it multiply by 3 H2O. Oxygen is also balanced because 3 plus 3 6. There also 3 2 are 6. It is completely balanced. See, like this. To write balanced equation compulsorily, right? Balanced equation. See, 3 phosphorus atom and 1 phosphorus. Therefore, P4. See, but this obtained phosphine is highly, it is not pure. So this will catch fire. It will catch fire and suddenly it will form diphosphine vapors. Remember, because it is having the garlic like smell. Root and garlic. Okay, root and garlic like a smell in impure form. Why? Due to formation of diphosphine vapors. Very very important for CET and for theory purpose. Suddenly impure phosphine form diphosphine vapors and catches the fire. Okay, highly combustible. So to make it pure, this phosphine is subjected to further it is treated with, okay, that is Ki, right? Sorry, first HI, that will form PH4I, phosphonium iodide. Phosphonium iodide is further reacted to potassium, that is iodide, right? And now here it will give out PH3, pure PH3 plus, right? That is this will react with in impurous form. This will give you phosphine. Okay, that is right. PH4, sorry, not the Ki. It is KOH, right? Sorry, extremely sorry. Phosphonium iodide, PH4I, Ki. okay, plus at least H2O. Like this, once again you get purest form of the phosphate. This will not catch fire and it will not convert into diphosphine vapors. That means phosphine is treated with a concentrated hydrogen iodide, converted to phosphonium iodide. These phosphonium iodide vapors are treated with a strong base, potassium hydroxide, where it gives phosphine gas, pure phosphine gas, and potassium iodide, and water is given. So like this, you can write for 3 marks if they ask in the theory for 3 marks. So explain the laboratory method of preparation of phosphine units. You have to write on this. First principle, this and this reaction compulsory. For 1 marks, very very important for theory purpose and for CET. Karnataka CET, and then even for sometimes that is NEET also. So this diphosphane vapors, especially, it is used as one of the important application, Ohm's signal. Ohm's signal. Ohm's signal technique. So what is this Ohm's signal technique? Especially in warfares, okay, that is in the sea war, warships, soldiers, if they miss any warships or boats, okay, then these soldiers, they will try to give the message to another soldier using this technique called as Ohm's signal. See, they will have, these soldiers along with them have what they have, tins. See, usually you will use now what that is cold drinks tin, no, like that, tins of calcium phosphide. Calcium phosphide, that is Ca3P2 and calcium carbide. CaC, calcium carbide. Things containing this calcium phosphide or calcium carbide, okay, they will pierce the hole and throw in the water, that is sea water. Suddenly it undergo hydrolysis. You know that calcium phosphide will give phosphine vapors in pure form, that will convert into P2H4 vapors and catches fire and gives it the heavy smoke. That smoke serves as a signal, that is called Ohm's signal. Even calcium phosphide also, this will give acidic gas, this will give phosphine gas. Okay, see, actually reaction is like this, H2O, now only you written PS3, okay, plus what you will get, CaOH taken twice, that is 3 and 2, this is 6. But here, what you will get, CaOH taken twice plus C2H2. So like this, generally you will have, see, just 2H2O, equation will be balanced. But C2H2 is also still in gas, that also catches fire easily and give heavy smoke. Remember, the tins or tinlets containing calcium phosphide, calcium carbide, when they make a hole and just throw it in the water, it will undergo hydrolysis to form phosphine, impure phosphine converts into diphosphine vapors. Even acetylene also catches the fire, they are highly combustible. Okay, right. Like that serves as a heavy smoke, serves as a signal for another, that is what? The soldiers. And with that technique, they will find out the missile ships, warships or boats. Okay, which is very very important in the warfare, especially warships. So that's about importance of this application in the warfare. That is diphosphane vapors. I will repeat, it is diphosphane vapors. Okay. Okay. Now coming to next another important properties, physical and chemical properties of this phosphine. What are the physical and chemical properties of the phosphine? Very simple. Physical properties are concerned, it's a colorless but a highly rotten garlic smell type. Okay, highly suffocating, and it is having rotten garlic type of smell. And this is prepared by, just I told you, white phosphorus with a caustic soda, right? And it is soluble in water. Sorry, it is insoluble in water. It is insoluble in the water because it does not form hydrogen bonding. hydrogen bonding with the water. It is insoluble in the water, but it will react with the acids HBr or HI to form respective phosphonium bromide or phosphonium iodide. The HI will form PH4i and PH4Br, showing that it is acidic in the nature. Okay. This is about another important property. Now, began with the cuprous phosphide. Okay, when they react this phosphine and mercury chloride, when they react this phosphine, they react with the copper sulfate and mercury chloride. They form respective cuprous phosphide along with cuprous phosphide along with the, it will form H2SO4, sulfuric 2PS3, right? 3CSO4, and generally H6 means it is 3H2SO4. Remember, this is called cupric phosphide. Even with mercury chloride also the same analytical form, mercury phosphide. See HD3, that is P2, but this time will form HCl. That is hydrochloric acid. 2 HCl, 3 HgCl2 and 2 PH3. So total will have here, which is a 6 means 6. They will form the respective phosphides. Okay, cupric phosphide, mercury phosphide forms when it reacts with the metal salts like copper sulfate and mercuric chloride. Okay. Even it reacts with the HBr, HI from the respective salts, PH4Br, CH4i, showing that they are Lewis. They are Lewis bases. Electron pair except Lewis acid character. Because see, it is having a deficient of one lone pair of electron. That is given by this one. And form how NH4i, like that PH4i, PH4. How ammonium iodide, how ammonia will form, like that same case, right? So that's about reactivity of this phosphine, especially with the other metals, copper sulfate and mercury chloride. Now coming to next more, there is properties. Next more properties we can go, that is almost these are over. Now structure. Now what is the structure of this phosphine? Structure of phosphine, one phosphorus atom is surrounded by hydrogen, and one lone pair of electron. You know that phosphorus is having 5 valence electrons. Out of the 5 valence electrons will share 3 with the 3 hydrogen atoms, forming duplet. 3 bonding pair, 1 lone pair. 3 plus 1 total 4. Okay, tetrahedral, but it is not tetrahedral due to the lone pair. It is pyramidal structure. Okay, it is having what? sp3 hybridization, but pyramidal. Trigonal pyramidal structure due to one bond pair. Bond angle is very less because of the less electronegative. The hydrogen 92.1 degree. 92.1 degree. Right? Remember, especially for CET, but not for theory. That's about phosphine. Now, coming to next another compound. Next another compound of the phosphorus, that is phosphorus trichloride and phosphorus pentachloride. We'll try to complete both because they are having common factors. Phosphorus trichloride, PCl, and phosphorus pentachloride, PCl. Let us compare the general method of preparations and even chemical properties, physical properties will compare and easily remember. See here. Method of preparation. Method of preparation. In method of preparation, see students, white phosphorus reacts with the dry chlorine, okay, and forms PCl3, 4PCl3. This is one method. This is white phosphorus on passing to dry chlorine gas, you get phosphorus trichloride. So just balance it by just multiplying about 6 This is one. Then second one, phosphorus with thionyl chloride, associated thionyl chloride also. You can prepare this. See. What you will get? Your target product PCl3, phosphorus trichloride, right? Along with it, you will give SO2 plus S2Cl3, dithionyl dichloride. Okay, once again balance it. 4PCl3, okay. Then SO2, okay. Then S2Cl2. Almost see it is a balance. 12, okay. And it is sulfur is 10 SO2 already written, okay. Sorry, it is 8 SO2 and thionyl chloride, chlorine 14 are here, 20 are here. To make the chlorine balance, just you have to prepare it. See, this is 8 SOCl2, 4 PCl3, sorry. 4 PCl3, 8 SO2, and what you will get is 2Cl2. 2S2Cl2. Sorry, it is 4 and 2S2Cl2. This is balanced. The phosphorus reacts with thionyl chloride and even it will give phosphorus trichloride, PCl3. Generally this exists as gas and even liquid also on combination. But see, it will produce here sulfur dioxide along with disulfur dichloride. This is method of preparation. The same case here. First one, white phosphorus, same white phosphorus, same white phosphorus when it is passed over dry chlorine gas. Even here also you can get it, but the thing is, you get PCl5, phosphorus pentachloride, 4PCl5. So it is again Cl. This is one. Second case, they will use P4 plus sulfuryl chloride, SO2Cl2. This is different. This is called sulfuryl chloride. It is obtained by taking sulfuric acid with excess chlorine. Remember, sulfuryl chloride. Here, what will you get? PCl5, phosphorus pentachloride, along with the SO2, sulfur. So 4PCl5 and 10 SO2. What will you get? 10 SO2. So oxygen also balance, chlorine also balance. This is the difference. See, you will get only SO2 there, but here SO2 and S2Cl2. These are comparison of what methods of preparation. That means phosphorus trichloride can be prepared by passing dry chlorine over white phosphorus. Even that is thionyl chloride over white phosphorus. Okay, but phosphorus pentachloride also passing dry chlorine, excess, remember, excess dry chlorine over white phosphorus, you get phosphorus pentachloride. But sulfuryl chloride because also you get phosphorus pentachloride. Only byproduct is SO2, but here it is SO2 and S2Cl2, dithionyl dichloride. Remember, okay, this is the method of preparation. Now if you go to next property, this is in the form of gas and liquid, but this is generally in the form of a solid. Gas, and but in a polymeric state it exists as a solid. That I tell you very important for NEET and CET purposes. Okay, right. Now coming to next other properties. This PCl3, it is insoluble in water, not reactive, it is insoluble in water, but it shows some Lewis acid-base character. Let us see how it will show Lewis acid base character, and it undergoes hydrolysis, especially in chemical properties. In chemical properties also you can compare both PCl3 and PCl with water. See, phosphorus trichloride undergo hydrolysis with the water and forms see, phosphorus trichloride and H3PO3, 3H2, phosphorus acid, phosphorus oxy trichloride, right? But this compound PCl5 first undergo hydrolysis in limited amount to form phosphorus oxy trichloride and HCl. Further, POCl3 with excess water undergo hydrolysis and form H3PO4. Okay, and and HCl. So 3H2, 3HCl. This is called phosphoric acid and this is called phosphorus acid. Very important. Dimeric and this is tribasic, as I told you yesterday. It's for 1 marks theory and for CET very important. That means phosphorus trichloride undergo hydrolysis to form phosphorus oxy trichloride and phosphorus acid, whereas phosphorus pentachloride will form, that is final product, with phosphoric acid and HCl. Remember. Okay, so that's about reaction. Then comparing another one. Lastly, another two chemical properties. We will also react with organic functional groups and from respective components, especially alkyl halides. See, phosphorus trichloride react with acetic acid CH3COOH and forms acetyl chloride CH3COCl. Along with this, byproduct will be H3PO3, phosphorus acid. Right? So generally 3 CH3COOH, 3 CH3COCl. The rest is already balanced. Okay? Right. H3PO3. Okay. 6. That's also 6. See, like this will form acetyl, that is chloride. Okay, that is POCl3 and H3PO3 and 3CH3COCl. That is right. 3PO3 and 3CH3COCl. Green atom. 6. Like this, acetic acid will react with phosphorus trichloride and form okay. That is exactly true. Okay. Next, we will also react with ethyl alcohol, C2H5OH, ethyl alcohol, organic functional group, and forms respective C2H5Cl, ethyl chloride. Okay, and once again H3PO3. 3C2H5OH, 3C2H5Cl. Like this, it will form what is usually reaction with that is organic. That means phosphorus trichloride reacts with acetic acid and form acetyl chloride and phosphorus acid. Even it reacts with organic group like alcohol, ethyl alcohol replaces OH by Cl, forming ethyl chloride alkyl. That means they form acyl halides and alkyl halides when they react with organic group like carboxylic acid and alcohol. That is a meaning. The same way, PCl5 will differs. It also reacts with acetic acid. Decomposes acetic acid to form CH3COCl, acetyl chloride, but along with this will form POCl3 and phosphorus oxychloride and HCl. This is the difference. Okay? The The same PCl5 reacts with ethyl alcohol. C2H5 OH form. C2H5Cl ethyl chloride along with phosphorus trichloride and HCl. Very effective. That's the difference. This is how we can compare easily properties of phosphorus trichloride and phosphorus pentachloride. Remember, okay? Right. So that's about reactivity of phosphorus method, general method of preparation and the chemical properties. These are the only chemical properties. But phosphorus pentachloride, it exists generally in gaseous state. But at a higher oxidation state, it changes to crystalline solid. It exists in two structures, one tetrahedral, one tetrahedral and one that is octahedral in halides. Okay. Right. In dimer form, it exists in the crystalline solid. But before that, I will just tell you lastly regarding this structure of PCl3. Structure of phosphorus pentachloride. Structure of phosphorus pentachloride is the same. It is also same. Chlorine. One. No. Since chlorine atom is more electronegative than phosphorus. Okay. Here the bond angle between these two is bonding pair of electrons 101 degree. There it is 92, here it is 101 degree. It is also same what there is sp3 trigonal pyramidal or just pyramidal also trigonal pyramidal or pyramidal with the bond angle of how much 101 degree. Very important for CU. Right, that's about PCl. Now coming to PCl5, structure of PCl5. Structure of PCl5. Phosphorus pentachloride, how it reacts. Phosphorus pentachloride, so it is having Cl. Right? Three are in the same plane. One above and one below. Cl. These are called axial bonds. And these are called equatorial bonds. Remember this PCl5, see it is 1, 2, 3, 4, 5 bonds. It is having sp3d hybridization. sp3d hybridization. Having 5 bonding pair of electrons. What are those? 3 equatorial bonds. Okay, equatorial bonds and 2 axial bonds. These are called axial bonds. Axial bonds are longer than equatorial bonds. Equatorial bonds are bond lengths are equal, but they are showing longer and more repulsion. Axial bonds show more repulsion towards this bonding pair of electrons. Okay, and this is what is the sp3d hybridization? What is the structure? Geometry is trigonal bipyramidal, which you already studied where in chemical bonding last year. Trigonal bipyramidal, definitely showing all bonding pair of electrons, sp3d hybridization, 5 bonding pair, out of that 3 equatorial, 2 axial. Axial bonds suffer more repulsion than that is equatorial bonds. Equatorial bonds, they are having 120 degree, whereas axial bonds that is 90 degree to each other. Alright, equatorial bond with the bond angle 120, whereas for axial bonds they are 90 degree. Like this is the completion of all the compounds of the phosphorus. See, that means today I have covered what? First one, that is allotropes of the phosphorus, white and red phosphorus and black phosphorus, right? Then phosphine, lab method, chemical property, then phosphorus trichloride and phosphorus pentachloride. This is a completion. Yesterday itself I already told you regarding oxides of phosphorus along with their characteristics. This completes the 15th group elements, right? Even including your need 20-21 syllabus. But for theory, what I explained today, that is compounds of the phosphorus, allotropes of the phosphorus, compounds of the phosphorus, is completely not for your annual examination. Okay, only for annual exam. But for NEET, you have to compulsory study. That's why I have covered it. Okay, right. Today we'll stop here. So once again, enjoy students and have a nice day. Thank you.